Hello and good evening, everyone. My name is Orithro, and I will be your host for today's session. Our today's session is Engaging the Universe, JWST, Infrared and Citizen Science. This is done in collaboration with SS Citizen Science Group, and the speaker for today's session is Mr. Suman Bhattacharyya. He is a senior research fellow, PhD specialization, astronomy and astrophysics. So, without further ado, I would request Suman sir to start with today's session.
So I'll take over from here.
Yeah, yes, sir.
Okay. Okay. My video and audio both are fine, right?
Yes, sir. The screen is visible, your audio is clear.
Okay. 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 So so there is like a two way of like we usually give a like a two way of presentation. So before starting, I just explain to you like what type of presentation this is going to be. So generally there is two way. One is like very much expertized. My means there we are not going to talk about uh, like intricate things like what is the general thing which is happening, but more like everyone we think like everyone knows everything, and based on that, what is the uh, that minute or recent updates. So that is one way of giving presentation, and another way of presentation where we are going to aware the audience or aware the people or the upcoming scientist people or something like who is interested in research or want to be do research, those people, to give them a glimpse about what is going on and how things are done and how much they can contribute, or even they, I mean, not just about contribution, but rather than they can build up their own career out of it. So this talk will be going to be the second type of uh, uh, discussion or second type of presentation, where I'm going to give an explanation like what JWST is, how this JWST telescope is so important in current astronomy field, and how a person who is not directly connected with this this community, this astronomy community, but still has enthusiasm, enough enthusiasm to do something. So what, how they can start contributing or train themselves. So let's begin. Okay. So primarily, what is the goal? Like everyone saw this JWST images and all, like how this JWST uh, satellite looks, this telescope looks like, and how they build up. What is the date of when they launched it? Everything we almost know this thing. So I'm going to avoid those things which we already know, but more let's conclude things how we what we can do using that telescope, or how much data is available for us. So let's first see what is the actual science goal for JWST. So the science goal for JWST is like to understand that end of the dark age, means when there is like everything was like a dot or something, like I mean just after that that big bang or something like that. So right now that theory is also become under question if it is there or not. So when that first photon start traveling, so when that photon start traveling, that is the end of the dark age. So to understand that when is that the end of the dark age happen, and when this dark age got ended, so this photon formed. That photon doesn't form normally. I mean, we need some medium where this photon got formed. That is something like we can see like some molecular cloud or something like that. That may occur. So those things are not going to stay on the in space like randomly. They have their own density. Basic physics law is there, so they will like start accumulating. They will start forming big structures. So one of that big structure is a galaxy. So understanding the galaxies is also a clue to understand the age of our universe. So galaxy formation and their evolution, like how that galaxy got evolved into what we see today. So that is another important science goal. Then birth of stars. So this galaxy formation is going on, like this gas is accumulating, but also in the microscopic scale, this dust or a gas is going to accumulate, like this one by one, this hydrogen, helium, then CNO6, all these stages will go through and will get the birth of a star. So this birth of a star is also a very important. But in the science cold case, the end of dark age and the galaxy formation are the most important, because birth of a star, that is very hard to see. But yes, JWST have that capability to observe at some extent. I'll come to that point uh, later. And life. Now we know JW is more like a infrared telescope, and we get a lot of signature in infrared. So this live detection is another crucial part of JWST. I'll also come to this point, like how they are going to detect the life using this telescope. I'll explain those later.
Excuse me, sir.
Huh? Yes.
So, what is basically dark age?
Huh. Basically, the dark age is something like this is that like before the launching, this was the general science goal. Like they have to submit a proposal. No, they have to ask for the money to make these telescopes, right? So this is something like that. So they wrote like the end of the dark age. Dark age means like that first photon, or that so first hydrogen formed. Before that, everything was like randomly floating around. The temperature is so high that no, not a single atom can exist. But when it started to cool down, okay, when it started to cool down, that hydrogen formed, and that transitions happened, and that traveling of the light started. That light got formed. Okay, actually light was there, but this is the light which we can observe. But in that kind of scenario, that light formation was one of the most important thing. Like when this light started to travel, so just before that moment is the dark age. So there is nothing. I mean, no light, but not just light. I mean, there is no concept of physics. Maybe there is no concept of, uh, I mean, thought or anything, because we don't know what is there beyond that singular point. Now, you got it?
Okay, sir. Thank you.
Yeah. Yeah.
Excuse me, sir.
Yes. Yes.
You said that there was light before, but light needs a like light needs a medium to travel. There
Huh.
was no medium over there.
Huh.
So how come you can say that there was light?
No, no. I said that medium because like that medium means who is going to form that photon. Like some transition need to be happen. No, some temperature difference or something like some energy transition where this photon will get sustained. Okay, so this is that v form, especially for that visual aspects.
Okay, okay, got it.
Yeah. Sorry, I think maybe I termed that wrongly, but it's not that medium. It's the medium for that formation of light. Okay. Yeah. So let's before going in depth, so let's know like after whom this telescope got its name. So this is James Webb, and he's the second administrator of NASA, 1961 to 1968, and he's a part of many large projects. One of them is that project Gemini. So he was the administrator for that also. So let's see, like we all know HST, Hubble Space Telescope. So let's have a simple comparison between Hubble Space Telescope and JWST. So how what is that upgradation happened here? So here we can see that JWST is primarily covering that optical region. If I move my mouse here, huh? This is that optical region, and it can go up to somewhere around 3 to 4 microns, something like that. So 30,000 to 40,000, I think so. I exactly not get that number, but something around that infrared. I mean, it's touching that infrared region. JWS, sorry, HST. Now, if we think about like what is the range for JWST, it is starting from somewhere around zero point 0.6, or you can take it as 1 micron, up to 26.3, or you can take it as a 30 micron. So you can see that the primary region where JWST is going to work is the infrared region. Okay, so why they selected suddenly this infrared and not like similar to JWST? That is a really interesting point, because as we have just discussed, like we are going to understand that first light and this galaxy formation and all those things. We need to see the furthest point, how far we can see. Okay, and we know from that Hubble constant that universe is expanding. So as a universe is expanding, everything is getting stretched out. So if there is a uh, galaxy or something very, very, very far away, and that galaxy emitted some light at like in a very, long time back, and that light traveled its journey towards Earth at that time scale. So because of the universe is getting expanded, that light also got stretched. So if some light is which is coming on like UV or optical or something, it's slowly getting stretched out and it's end up with in the infrared region because it's stretched so much. So to see the furthest point, we need to see the infrared in the infrared light. So that's why that is the primary reason why JWST is dedicated. JWST is more like a dedicated infrared telescope rather than optical. And obviously, you can see from this image the size of the mirror. It's almost like 6 meter for JWST and almost like 2.5 meter, 2.5 meter for HST. So you can understand like the light gathering power is tremendously high, almost somewhere around 6 to 7 times more in the JWST, and it needs to be high. I'll come to that point later. So by this, we can see a very much high resolution in the images which taken by JWST. So here we can see the top one. I didn't wrote any HST or JWST because just by looking at it you can understand like what is the 1990 and what is 2022 looks like. So you can see that resolution is hell and heaven differences there. We can see a lot more stars in the background. So this is how important this JWST is. And also, if you see carefully, we can see a lot of intricate structure which was absolutely not available in that HST image, but here in the JWST we can actually see. Actually, our work is more lenient to that point to understand this kind of gas structure and all. So I have two slides where I have explained like how we use these infrared images. So
Excuse me, sir.
yeah, yeah.
Sir, as you are comparing HST and JWST images, I have the question that could we have had more high resolution pictures as more than the what JWST produced?
Can you repeat? I didn't get it.
Yes, sir. As you are comparing the HST and JWST
Huh,
pictures,
huh.
so could we have had more high resolution pictures of what JWST is currently producing?
Yeah, yeah, yeah. I mean, this why I'm showing this image because this is the most popular image. That's why. But there is also like multiple images. There is almost like more than uh, 2 lakh by now. There is 2 lakh data. This data file is already there, uploaded in the archive. Okay, from JWST only JWST. So I'm just showing this here now. But out of that 2 lakh, almost like I don't know exactly number, but it is somewhere around like it's quite adequate number of files are image file and others are spectroscopy file. Then this coronagraph, then this time series spectrograph. Multiple files are there, but there is like more than 2 lakh uh, data files are already uploaded in the archive. I have one. I mean, I'll show you like how to fetch those data from the WST. So I mean, you'll understand like how to fetch those data and observe by your own eyes, something like that. So yeah,
Okay, okay, sir.
there are multiple images, high resolution, lots of images. For here, I'm just showing one for representation purpose. Yeah, but yeah, one thing you have to understand. You cannot discard HST like okay, JWST is so good, HST isn't bad. No, no, no. That is not the case. In astronomy, how we are going to do it? Something like HST launched a long back. So the catalog or the data that HST have is a lot more than JWST. So we use this JWST as a complement to that dataset to get new science out of which science already got published using HST. So we are refining things also. So these two are very important telescope in the sky, but we can see that what this human brain, how that got developed, and what things we can actually produce to make our science more accurate. Okay. So before going more into that, like how to use the data science or something like that, it will be bad if I'm not going to talk about the instrument there, instrument in the JWST, like how they are working, because JWST is a telescope which is not just like, you cannot say like, okay, this is a great achievement for the astronomers or astrophysicists or some or scientists. No, this is something like a huge leap for scientists, biologists. Then this, I mean, who is going to use the data for then engineers and I mean many more. So this is something like accumulation of multiple fields in one place. Now here, one fun fact is that, I mean, a few days back I had a one meeting. So many people still think like JWST is using some mirror, glass mirror, but in actually no. uh, JWST mirrors are not actually like a glass mirror, like which is there in Hubble. So it is actually metal, beryllium. Beryllium is a metal. So they used beryllium as a as a glass in this case, and they coated with gold. Now you may ask why gold? Why they used some other coating? If you think carefully, why the color of gold is gold color? I mean, if you think it, that's mean it's a bit reddish, like that red is a gold, especially that gold color. I mean, I don't know how to explain that, but it is a goldish color. Now that indicates that the hue or that reflected light which is coming to your eyes is more shifted toward the red region. And if you check thoroughly in, I mean, using scientific instrument, you will see gold has that gold has this property. It can actually reflect infrared light more efficiently than optical. In aluminum coating is vice versa. It is not very much effective in case of, compared to gold for infrared, but very much reflective in case of optical. But as JWST is going to observe in infrared, in this case they used gold as a coating. Now, and they used beryllium just because of to save weight, and also beryllium they can flex it. So this telescope, like in JWST, in HST, some issue happened when they launched it. That telescope was not in proper focus. That images are not proper focus. But in this case, because they cannot go there and repair it, so they put it. They used beryllium also to make it a little bit flex so that they can alter the focus point for each mirror. So yeah, so there is a lot of science and engineering going on behind this mega structure or mega project, you can say. So let's talk about the instrument, which is by I mean going to used by the JW, which is using JWST is using for its observation. So you can see there is like four main cameras are there: MIRI, NIRCam, NIRIS, and NIRSPEC. I'll just go shortly along through this point. MIRI is an infrared instrument. It can take image as well as it can do spectroscopy. It can observe like up to like around 5 to 30 micron. NIRCam can do zero point 0.6 to 5 micron. Whereas NIRIS and NIRSPEC both are only dedicated for this spectrograph. NIRIS can also do image. Now this spectrograph, I think you already have a very glimpse, basic idea about spectroscopy, like where the white light is coming, we pass through it through a prism, and that light split it. So you can see this rainbow color. Similarly, when this infrared light comes, we can do the same thing. When infrared light comes, we can split it into multiple infrared lights. And in that infrared light, we see at which particular infrared line or color is missing, or which color is high, low, or something like that. Based on this accumulated information, we make a spectra, like this wavelength versus intensity. And by that, we can understand like what material are there in the object where this infrared light is coming. So here you can see this. This is the conditions. I mean, this is the checklist of what MIRI, NIRCam, NIRIS, and NIRSPEC can do. So you can see this imaging can be done by three: MIRI, NIRCam, and NIRIS. Why I'm saying imaging specifically, because the work we have done or we are doing mostly into the imaging part. Spectroscopy, this thing will come later. So for this talk, I'm only going to fix it up to imaging. Okay. And this is that this image of the structure where this four instruments are placed. So you can see why, again, as I explained, why infrared observation is very much needed to understand the universe. From this image, you can see that he is part of the team of Spitzer. Spitzer is another infrared telescope. It can go up to like almost near to 100 microns, something like that, 100 micron infrared. But the problem of Spitzer is that its telescope size is very small. So that resolution is not as good as JWST within uh, this 30 micron range. So, but okay, that apart, we can see. Okay, let's concentrate on the image. We can see that this guy is holding a like a plastic paper or plastic sheet or something like that. But in normal, in optical, on that left image, we can see that his hand is not. I mean, you cannot see his hand because optical is that plastic is making. I mean, is opaque to the optical light. Means that optical color or optical light cannot pass through that plastic. But when you shift to the infrared, we can clearly see his hands underneath that plastic paper. Why is that? Same thing. Because in the infrared, that light is so much stretched out that the small holes or the gaps in the plastic is quite large enough for infrared, but not for optical. So optical were blocked easily, but that holes are quite big enough for infrared. So infrared can easily pass through the plastic, and that is one of the main reason like how this longer wavelength of light we need like larger telescope or something like to make observation. Okay, I mean that is more into that scientific case. So here this is the primary reason why we need infrared to see farther. Also, if you see this image carefully, that guy is wearing one glass, and you can see that glass is transparent. Like I can see his eyes in that left image, but not his eyes in the right image. Now this is another interesting thing. Optical can pass through, but infrared cannot. So this is the way. I mean, this is the like a property of the universe. So they are giving us so much clue to understand the universe itself. So here you can see that glass is having this uh, structure that the light can actually pass through, but infrared is not. Infrared don't have that opacity or have that transparency enough that it will can pass through the glass. It will block. That's why if you see in army or something like that, they always wear this big hats and all. There is some camera attached to their helmet. Those are actually infrared cameras, because at night maybe you cannot see anything, or even if you have a very high sensitive optical camera, uh, I mean still that maybe that enemy is like hiding underneath some cover or something. You cannot see in optical high sensitive optical camera at night. But if you have an infrared camera, you can see actually, because that heat is coming out of that region. Though he is under a cover, but that cover is transparent when you are observing in infrared. So that's why infrared is again a very important thing in any army or any country.
Excuse me, sir.
Yeah.
Sir, the man in optical is we can detect the colors that he's wearing which color t-shirt and pants, but in infrared way
Uh-huh.
everything is reddish, as orange reddish. Why?
Yes. So what is the if I ask you like what is the color of UV? Can you tell me?
No, sir, I don't know.
No, no. I'm just you can think about it. Like, what is the color of UV, or what is the color of exactly infrared color. The main thing is that we don't know that. This is all our false color. Means our eyes only have this property to observe the optical light. So that is the true color we can see. But other than that, all colors are not visible. So what we do, we use false color. Now, suppose you have a person who is like color blind or something, like he always like what you are saying as green, but that person will see that color as a red or something like that. From his perspective, it is actually correct. That is the red. But from my perspective, it is blue. So from each person's point of view, that color exists. That is that essence what your eyes is making. Now, that is only possible in that optical range. It is a very short range. In that optical range, like blue, yellow, green, red, done. But after that, infrared, we have no idea. So what we do? We do the intensity plotting or something like that. So here, what is happening? Like you can see, his head is very bright, but his waist is not. Why? Because his body is hot. So that, I mean, obviously the blood is flowing, so blood is having temperature, and any hot object will emit and infrared. So when there is an exposed body part is there, that will emit more infrared, but these regions are comparatively obstructed by this clots and all. So we cannot see that glow in his body. So that's how we made this intensity, means that what is the hot region and what is the cold region. Like that, we make this kind of image. But in actually, the color concept is not there. We only use like more like a wavelength. Like this is working on something like 2 micron or something like 1.6 micron image. We say it like that. We don't say like this is a red image or this is a blue image. In optical, we say this like this is a green filter, this is a red filter. But when it goes to infrared or UV, which is not observable by our own eyes, we use number like wavelength. I hope you got the answer, right?
Yes, sir. Thank you, sir.
Yeah, yeah. So yeah, now this is the image like how this spectroscopy works in JWST. So I'm not going in depth in this case, but just for some line, like when you pass through that infrared light which is coming from a source like a star, which is there is a planet rotating around it. So in a certain configuration we can take the spectra, and in that spectra we search for some lines, as I just told you that that infrared light will come through and it will go through the grating or something like a prism, that and that the light got splitted out, and we can see the multiple wavelengths which is accumulated in that one beam of light which is coming from the source. Now, in that beam or in that splitted light, we can see some wavelength, the light is less, in some wavelength, the light is high, color, the intensity is high. By that, we can make this kind of a plot, intensity versus wavelength. And in this plot, we try to see if there is a hydrogen, because we know if in water. So if we know in the lab we have already experimented, like if or water is there, what kind of infrared light water will make. If carbon dioxide is there, what kind of line carbon dioxide will make in infrared, similar to methane, something like that. And that's how we utilize the spectroscopy in infrared and to understand the life in other in faraway planets or something like that, exoplanets. So this is another science goal for JWST, and it is really doing excel in that field. So these are the general things. So I'll give you a glimpse like how actual work we are doing right now. We cannot do, obviously we are like particular part of some particular team, so we will do a particular task using the JWST images. So I'll just give you a glimpse about like how we use these JWST images and what work we do. So you can see this is the image I used for my science case. So here the thing is that you can see there is 6 images: F90, F187, F200W, F444W. So these all are actually name of a filter. As the question asked, like what is the, I mean, why that image is not colorful, right? That this is the main reason. Because that color we cannot perceive, like what color is that? So we use number. So that's why all these filters are having name, or that, and these 47, and these are indication of the wavelength, that what infrared wavelength can pass through that filter. Now you can ask, like, sir, then why this colorful images? Like, what is the color means here? Okay, this color, I intentionally I change the color in each filter image so that I can separate them out. If I make a black and white every one of them, all six are black and white, so it will be hard for me like to understand image this separate properties of these images. So that's why we put different false color. These all are false color. So to see like what is happening in this object. Now, if you see carefully, this is a star. Maybe this is a star. Maybe inside that some gas structure or something like that. In F95 W filter, we can see it's a very small dot. But if you come to this 444, we can see this big wall or this big region. So it is quite bright in this 444 filter. So what it said? So we can say like in the 444, this filter, that layer or that whatever is there in between that object and our line of sight, maybe that is more transparent in this filter, but not in this filter. So we can see this star very bright, but here not so bright. And this is the main property we use a lot of time, a main property we use for JWST to understand multiple structure in stellar or in molecular cloud or something like that. So recently we published one paper on understanding a structure of this GUM31. This this is that famous image, GUM31 image that JWST published. So in that image, we have tried to understand that how these shocks are working. I'm not going to go more in detail, otherwise it will be hard for me to explain also. Like, so you can see, as we just say in the previous slide, like multiple filters show multiple depth. You can see in the HST, when we use HST image, we can see this gas structure and all fine. We cannot see a lot of background star or something in this image. But if you go to this one, when you use this F444W filter from JWST, you can clearly see this layer got little bit of like transparency kind of thing. We can see a lot of background star, and maybe this same field, background field, is actually passing through this region, through this gaseous structure. And we can see, and by this comparison, we can actually understand the depth of this molecular cloud, something like the structure inside it, and that is what we have done here. And this is another two filter, like we have just measured two images from 470 and 444 filter, and we just minus the intensities from those two filters, and we made another hybrid filter. So that's how we do this work to understand the structure. And using this image, using this information of the structure, we can understand the star formation. Then what is that shock? How this shock is getting formed? What kind of structure a molecular cloud can have? Something like that. So what is there from the citizen science point of view? Now, all these things are more like a bit more like a specialized thing, or something like, okay, if I want to do this thing, I have to be a part of a large institute or something like that. Yeah, it is true. You have to be. But why? Because of the facilities. You need that facilities. Suppose you are doing a many, I mean, you downloaded lots of JWST images and you are going to analyze them. That is a bit hard to do in your laptop or in your computer, because one single image size is something like 5 GB, just a one image. And like that, there is like maybe 10,000 image by now. So you can understand, like, there's a lots of constraint is there. But still, if you think you can do something, go ahead, you can actually do. So I'll just give you a glimpse like how to do these things. So before that, I have one slide. You can note it down, or you can do the QR scan, so you can get these links. So these are some interesting links, like the description, like who is this James Webb, why his contribution is so important, and then this general science about JWST image wizard. Like you can download multiple codes, then softwares to analyze JWST images. Then this sorry, then this catalog filter mask where you can download JWST images. Then this is my research gate link, so you can go there and see some papers like how things are getting work done. I mean, how we are going to use this and how this paper get published, something, what kind of science we are producing. And then this is the current paper which we just showed before, this last paper that published. So this is the link. So you guys can scan this and you can get all this information, or you can write it down somewhere. Because now I'll go to the browser so I can show you like how citizen science aspects come into the JWST images, or not just JWST but also HST images. So we cannot just deny like we cannot do anything using like hardcore, like who is only part of some science case and they can only perform good things. No. So we can see this the story of Judy Smith. She was a part of this citizen science project of Duster, then Disk Detective. I can recall like multiple people from citizen science group is also part of this group. I think Disk Detective, they have done work in this citizen science project, and she have done this JWST image wizard. Now you can go, it is already there in the list, so you can go and read about her, like how she has done this. So I'll just give you a summary. She's a part, I mean, she knew like how to do this image analysis. She know about Photoshop and all. And so she started downloading these JWST images and tried multiple filter combination and all. And she was trying to see some structure. If that structure is coming out using some particular filters, but not using all the filters, or maybe that feature is not visible in one filter. So that's how she tried to combine multiple filters, and she started seeing different kind of properties from the objects she was downloading the image from, like the objects for what she was downloading the image. So by that she's already published. I mean, she was a part of the work. I mean, his colleague. I mean, she has published one paper, I think, in Astrophysical journal later. So you can see like people are doing work using image processing. So this is more like a image processing. But if you want to do spectroscopy using JWST, it will be a bit of hard. So I will not recommend exactly at this moment until or unless some comments are coming from JWST team itself. So, but image processing definitely people can do. So how to do this JWST images, and what is the primary goal, or what can be achieved by using by doing this image processing? So to understand this disk structure and all, as I just said in that images, in the previous images, that you have to understand like how to combine the filters, how to orient the filters, how to manage manage the filters, right? How to combine them actually using proper coordinates. So then you can start seeing that one star is visible in one filter, another filter it is not visible. Now you can understand the 3D depth information, like where that star or what is the size of that molecular cloud in that z axis or that line of sight axis. So you can do a lot of thing actually. Now this is the link, it is already mentioned in that slide. So you can go there to read about the more in-depth properties about JWST. And now this is the main link. So this masked link, that I think that fifth, yeah, no, the third link. Here actually you can go and download JWST images. So I'll just give you a small demonstration, like how we can actually download. So you can go like mask website. When you open, if you click on that advanced search, you'll get a link like this. Here, object name or position, you can just type like what object you want to see. Uh, So I'm selecting GUM31. It's a molecular cloud region. So you can see now it is start searching for record. and you can see 10. Okay, sorry, I mistake one thing I didn't say. In the mission, just below object name, in the mission, you can see there is a list of objects are there, and you have to tick on the JWST. Yeah, just like this. I have already ticked it. So JWST. So you can see there is already like above 2 lakh data sets are there, data points. So you can do a lot of things using JWST. Now after it will show you the record found 10. Now you have to click search. Now you have to wait a little bit. It will open a tab like this, masked, advanced search. I mean, if you have do multiple searches, then it will 1, 2, 3, 4. So I'm doing it for the second time. So you can see it is number 2. Now you can see these are the images or the data files, sorry, or exactly to be exact, the data files for whatever the JWST has been obtained from that direction. And you can see it is marking that region. You can zoom in what region that JWSTs actually have been observed. If I click here, so I can see like the visualize. So you can see the visualize option is there. If I click here, this is the minimum recommend search through the dataset. I don't know like if it is available right now for the see my net is slow. So I mean in general you can like click by clicking here, you can actually download the files. And there is another software called DS9. And yeah, cow image DS9. So you can download this software. It is available for Linux and Windows both. Whoever is having Windows, they can go and check that. And this software is enough to open the FITS file, which you are going to get. Okay, I think there is some issue with my network, so I cannot show you this. But yeah, when you download, you will get a file like this and end with .fits. Okay, so by this way, you can download multiple images and you can just double click and open in DS9 image. So it will show you that image, what you have downloaded. And then you can do a lot of things by changing the this color tone, region marking, then the intensity mapping. You can do a lot of things. But I mean, that I cannot go through in this like limited time. So I cannot explain this thing, but there is lots of YouTube or later we can arrange one dedicated class on DS9 only, like how to use DS9 to observe or to see or basic understanding of JWST. We can do later also. But this is how you can download. I myself, I'll suggest, I'll say like I have to say this because I myself started using randomly. I started downloading HST images similar to this. You can actually in when you clicked on this JWST mission, you if you tick in HST, it will show you the data whatever is available for HST. I randomly I downloaded HST data, then I opened it and I started playing with the images like how this filter works, this thing, and I got more interested. I mean, I really got like the images looks beautiful. Then I start searching in internet like how this thing is working, who are actually using this kind of images, what kind of work it is going on using these images. And slowly I understood like, okay, so this is how HST, JWST images are working. So from a citizen science point of view, anyone can do this, but this is more like a interjecting like their self-training here because this is not a like a thing like a citizen science project at this moment. So this is more like not a target based, but this is more like a very core science based. Like if you able to see anything, any intricate property, obviously for that you have to understand that kind of structure, like what this structure means. Hello.
Suman, I have
Yeah.
a question.
Yeah, sure.
Uh, my question is that if JWST recently take a image,
Hmm.
so how we know that image recently take it?
You're taking, you're saying like what time it will take to make
Yes,
JWST image
yes,
public.
recent image. If
Hmm,
suppose JWST today
hmm,
take a
hmm,
Andromeda galaxy M31 image is
hmm,
taken
hmm,
today.
hmm, hmm, hmm,
So how I know or this image
hmm.
available in MESS portal?
Okay. So there is actually timeline. Look, JWST is something like is a proposal based. As of now, it's a proposal based telescope. Means uh, scientific teams need to submit a proposal. Okay, to see the to use the JWST. Okay, this is not like a survey telescope. So you can actually like search. I don't have the link right now with me. So they have this like what kind of observation JWST is going to do in the next year. Okay, that list is already there. You can just Google search it. Okay, that is easy. But by that you can understand like okay, this time they are going to take the images and they are going to process it. I don't know exactly what's the time they will release the images. I think it will be somewhere around 1 year maybe. I mean, after taking the data, 1 year they will allow it, then it will make it. They will make this image as a public or something. I mean, that is I assume something like it could be less than that also. That I don't exactly know the number, but they will not do it immediately. They will give the chance to that observer because they have already took the data. They have to reduce the data because I mean you can understand if you are getting the absolutely raw image, uh, you cannot do a lot of things. You need that at least some processing. Those people can do this, and then they make it public. Then you can do a lot of things out of it, right? Yeah. So yeah, I was there. Yeah. So in this case, so one thing I would suggest here in this kind of thing. So from my perspective, when I started, I was in school at that time. I used HST images, and I tried to practice myself. Like if I'm able to do this understanding of this RGB images from HST, am I able to make this proper fitting on like two images based on their coordinates, something like that. So it was more like a self practice. When I came into research, those knowledge actually helped me. So here, actually, this is exactly citizen science scientists can do this, but students in this group, the students who are right now in school or in masters, and they're thinking about like progress into the, I mean, do their future or want to make future in the astronomy field, this will be a very good add-on in their portfolio. Like they know image processing or something like that, or basic understanding of the filters, basic understanding of how to do this image fitting. So this will be a very good practice for them to make a better future for themselves. So this is exactly citizen scientists can do, but it will be very useful for the students specifically. So you guys can actually like I mean go through this link. You can read through it like how these people have done, and also in ESO and NASA they every year they publish they actually arrange multiple competition like where they will ask you like to take some particular images from HST or JWST. Maybe that JWST will come up because it's happened recently JWST. So HST was there, so you can fetch the data image data from their catalogs, and you have to make proper processed image using those this telescope images, not taking astrophotos or something, but taking the images from that masked portal. And you can submit, like I think she got first or third, something like that, but I mean she won the prize. So similar to this, I mean this target, I mean this practice will really uh, make, I mean for student it will make some good contribution in their career, and also for citizen scientists it will be gain some very good experience, understanding of images, image processing, and obviously paper is there because lots of people need person who knows image processing in more efficient way. Like if you know better, then obviously you are efficient. So that's something like that. So Yeah, so you guys can scan this or take note down this website, so you can go there and fetch the information what I just explained. And then thank you. So if you have any question, please, I'm ready to take the questions.
Those who want to ask their questions, please ask them right now.
Good evening, sir.
Good evening.
Sir, you said that there are citizenship opportunities. Is it only in universe you're talking about, or any other platforms are there separately for the JWST?
Right now, JWST haven't done any separate platform to do like this. I mean, uh, this image processing and all. There is no dedicated website for that. So the website I showed you, that same website used by professional people as well as citizen scientist people, both, because there is lots of amateur astronomers who actually helping astronomy community. I mean, the people from astronomy to do their image processing and all. So I cannot say you like there is a dedicated website, but you have to go there. You have to deal with this more professional tool now, and you can explore this. And there is a lots of tutorial available online. So it will be really a great experience. I can say, like, if you have that dedication, it will be a really good experience. Like you are doing something totally out of this. I mean, more like out of zone something. But obviously, this needs a bit of more power, better laptop or computer, something like that, because you can understand this is some image processing you are going to do. So you need more RAM or something like that.
So we need to report the same thing to the JWST website. Yeah, that means something we are processing the image, and we have to report that image to the same website or somewhere else.
Okay, for that reporting thing, this just a second. Yeah, so reporting thing, it is not exactly a reporting thing, is that at this moment. Okay, because the thing is that, I mean, you have to understand this thing. I mean, image processing is a next level work. I mean, this is not something like it will not take maybe 1 day or 2 day to do one image processing. It can take something like more than what to say, like more than 1 month to do one image processing better way. And then you can directly approach, like in that star, like, or that in that region where you are doing this image processing, you can clearly see like which team in the astronomy who are actually working on this. You can approach them directly to show them like this kind of processing we have done and something like that. So this is more like, because look, this is a vast open thing. Target, I mean, there is a lots of thing you can get from JWST images. So in like a citizen scientist citizen science this projects, something like that, there is a dedicated one single task, like you have to detect this one single object. But in this kind of thing, you are going to get thousands of things. So it is quite hard to put it in a simplified way. But if you have capability enough, or I mean, you are dedicated to spend some time with the images, definitely you are going to get something out of it, and you can ask directly to the teams, like if that can make any contribution or not.
So it takes a bit of 1 month time. So is there any tutorial available in the website?
Yeah. This is already there in the list. So if you go there here, you can see JWST user documentation, JWST pipeline documentation, archive manual. If you go through this, they are going to give you the codes. Then there is some simple programs are there where you can open. But I would suggest DS9 is the best one. So here it is like understanding JWST data, where it will inform you, like when you download this FITS file, it will explain. There is a like multi-dimensional data file, FITS file actually. So in that file, what column means what, everything is written. So you have to understand like, okay, this is the information of the image. Then you see like, okay, this image is having lower intensity. Then you can go back, delete that image. You can download another image, something like that, which is having a proper intensity. There's a lots of opportunity in this kind of images. This is the pipeline documentation, like how uh, after taking the image, they are doing the proper first like calibration and image processing and all those things.
And I was there in the Spectra Police when you have started it some 2 years back, and it took a lot of time to start. And when meantime, when you announced that Spectra Police is going to start it, at that time I was not available, and I could not join in that. Is it working now? Is it going on now?
Okay, the Spectra Police actually, we had some issue in during our execution of the Spectropolis whole project. So we had some issue because of that. There is a not of like we are doing our PhD work. Okay, so we got involved in multiple projects and all. So somehow we got so much involved in this works, like we are not able to make proper time for that, and also we need more human resources, where like everyone of us got busy with our work. So we are spending our time to make this Spectropolis more easier for people to approach. So we are actually making a dedicated website for that, and and we are not going to give the direct raw data to the people, but more than we are going to do a little bit processed data, so it will be easier for everyone. So we are uh, more like recreating that Spectropolis thing in the, I mean, like next level, because the previous one was not up to date and it was like beyond our capabilities. So now we are targeting for much better way of doing. We'll announce like when it will get released actually.
Okay, thank you, thank you.
Yeah.
So why, like, is there any advancement done by JWST in Big Bang theory or something about the universe?
Yes, can you say again? Repeat that question.
In Big Bang
The,
theory or before universe?
Tanushka Bhatnagar. Yeah, yeah. Okay, so you're saying like, is there any discovery about Big Bang theory?
Or anything it has proven before universe, something like
Ha.
infrared rays.
Yeah, yeah. Few days back, there was a report came, like one paper came out where people are saying like JWST break the like the basic ideology of like the age of the universe, right? You're talking about that, I think. Yeah. Look, the thing is that, I mean, I'm not exactly in that like cosmology oriented work, but that paper actually what the paper actually signifies is like something like when they do the observation, they observe that some light, I mean, you can I can say you like, as I told, if as the universe is expanding, that light which is coming from very far away will also get stretched. Okay, and so when it is light got stretched, it will go from blue to red. I mean, high wavelength to low wavelength to high wavelength. It will go. Now they saw like the lines or that feature they are able to see using JWST. That feature maybe should be there somewhere in that far UV or something like that. And if when they measured it, like, okay, how much shift happened, that line from where it gone came to infrared, what travel it, I mean, what the distance it travel in that wavelength scale. Based on that, they understood, they measured that age, like, that per year how much expansion is happening in our universe. So based on that, they convert that into age, and they found that is higher than the this Big Bang scale. Uh, and I mean, that theorizing, like it could be some error or something like that, but still that needs more in-depth analysis for that. So yeah, it could be. We don't know because till now, Big Bang, everything was theoretical. And now we actually have an instrument which can observe. And when it saw this, it's already started knocking on that limit of the theory. Like we don't know like if the theory is correct or wrong, but whatever it is saying something near to the theory, something like it is higher, it's lower, but somewhere around it. So we don't know. In future, maybe we'll get something like maybe that Big Bang theory, the time scale is actually higher than that. Maybe we don't know. So yeah, we have to wait a little bit more because lots of data already have been. I mean, JWST already took taken. I mean, already took. Processing is going on. So maybe later those paper will come.
Was like, where can I find those?
Papers.
Yeah.
Okay, and that's a very good question. Okay, I didn't mention that, but you guys can actually type down. I mean, or write it down. This website. I mean, I'm just giving you that exact website what I used. This is something like archive.org. Cornell University. Archive, arxiv.org. I think many of you may know already about this website. Here you just type JWST and click search. If you do this, you will immediately get a list of paper from present to the like whatever paper is there registered. So you can see showing like almost 2,231 paper where this JWST word has been used in the abstract or in the title. So now you can see like you can see like lots of paper that came out. I mean, these papers are maybe this paper maybe came out today, something like 27th September. What is today? Okay. Last paper came out on 27th September 2023. So if some one paper came out today, that will show here.
Suman,
Yes.
this research paper available for download?
Yeah. That's I
This
mean,
website.
yeah. You can see there is a PDF written. No, just click. I mean, obviously, yeah, you got that PDF. Now you can read through it. Obviously, I mean, I'm not saying like everyone will understand this paper because these are like some specialized paper or something. But at least you can get a glimpse, like, okay, uh, what type of work is going on. At least try to understand that conclusion or abstract, or at least read the introduction of the paper. So here they are saying like JWST reveals a luminous infrared source at the position of the failed supernova candidate. Really interesting. I mean, I haven't read it yet, but it's really interesting. So you can understand. So they have written the gist of the paper, like what work they have done in this whole paper. This is abstract. Then the introduction. At least try to go through this introduction part. Here they are going to explain things in a more simple way, like what kind of data they are going to use, why they are selecting JWST, what other data is there for the same object or something like that, why they are saying it as a failed supernova candidate, something like that. And it will be really fascinating. So you guys can go there and simply just download the PDF. I mean, you will get the PDF immediately, and you can start reading.
Okay, thank you, sir.
Yeah, no problem. So, any more questions regarding this research-oriented thing? I'll be happy to answer because research is available there. But I mean, you have to
Sure.
go there, download. You can start reading, and even
So, is there anyone who can help with before a Big Bang theory or something? I have to publish a research paper, but I'm not getting a mentor for that.
okay. I mean, can you repeat that? Your voice was cutting off. Can you repeat?
So, is there any? Can you help me out with the before Big Bang theory on a research paper?
Hmm.
Because
Okay.
I'm
So
not getting a mentor.
okay. Okay, so I am more into observational astronomy. Okay, the field you're talking about is the cosmology. Okay, so you can see as I just go one step back, You can see there is an archives link. I mean, though I searched it here as a JWST, but if you go below, they have separated out under physics. I mean, not just here. Even you can suggest your friends who is more like getting interest into other field like material science, high energy, nuclear experiment, or something like that. Computational physics or something like that. You can see there's a lots of field. You can suggest them also. And as you were saying, the cosmology, black hole, those things. Yeah, you can go here like under astrophysics includes astrophysics of galaxies, and the second one cosmology and non-galactic astrophysics. If you go there, it will show you the recent astrophysics paper. Okay, so just I mean, I can arrange some people like with whom you can actually have a discussion about this cosmology thing. But exactly, I don't have that much idea. But I'll try to see like there are some people or teams or not even that. Even there is some portals are there where this cosmology oriented work is going on. You can approach those also. Just keep in touch. I mean, we can figure something out. So, I mean, are you in, I mean, MSc or PhD something?
I'm currently doing my BTech, but I have to write a research paper as a part of my project. So that is why.
Oh, in BTech.
Yes.
Oh, in BTech you have to publish a paper. I mean, that's an interesting thing. I mean, I never heard it, but that's good. But I mean, if you're in BTech, then I mean, okay, got it. I mean, but I mean, BTech we should be like observational. I mean, I thought like, okay, you're doing in cosmology. Yeah, fine. I mean, you go through this link to get a basic idea like how what is the level of work people are doing. Okay, before starting, I mean, I I think you should get a idea like uh, what level of work people are performing at this in publishing a paper in cosmology. Okay, so I suggest you go through this, give a little bit of reading first, and then you start approaching. Is that fine?
Yes, sir.
Yes,
That's a
good,
big
good,
help.
good. So any question?
Okay, so those who want to ask their questions, you can ask them right now because we'll be ending the session soon. Sir, I think someone is asking a question in the chat.
Okay. I think I just answered this question actually.
Yeah.
JWST and how it helped us to with the formation of the Big Bang or starting of the universe, and it is not.
Sir, this question was posted
Ah,
before.
ah, thank you, thank you.
Okay, so guys, so if you want to, it would be great if you like show your enthusiasm or how you liked the session. You can just post it over here by commenting that how you like the session. Just write down your comments. Okay. Okay. And lastly, before ending the session, I just uh, give you a recap of what what we had in the session. So I would like to thank Suman sir for the presentation he had today. And I would like to thank everybody else who joined the session.
Thank you.
Thank you, everyone. It was nice.
Thank you, Aritra.
Yeah,
I
thank you.
mean, for this great session. Yeah. So should I log out?
Yes, sir. Yes, sir. You can now.